Hello, I'm Jingjie from the University of Wisconsin-Madison. Today, I'm glad to talk about our KALEIDO, which is a real-time privacy protection system for eye tracking applications. So first, what is eye tracking and why should we care about eye tracking? In eye tracking, the user's eye gaze location or attention is being checked continuously on a visual scene by vision cameras. For example, when you're visiting Vancouver virtually for USENIX conference. The eye tracking is an emerging human-computer interface, and it is equipped with a lot of rising mixed reality platforms such as Microsoft HoloLens. The eye tracking enables hands-free interaction between the human and the machine. The applications include social avatar, foveal rendering, event triggering, and so on, that can improve the user's experience in mixed reality. So what's the concern of using eye tracking data? Before going into the detail, I would like to talk about some backgrounds about eye tracking data. The eye gaze data is essentially a streaming data type of timestamp location tuples. And the region of interest on a visual scene, such as the web elements, can attract human eye gaze attention. The eye gaze data is characterized into two major types of events. The first one is the fixation, which is a cluster of concentrated eye gaze that represent the human attention. And the second one is the saccade, which are gazes traveling rapidly from one fixation to the next. So what's the concern here? Actually, the eye tracking data is telling us information more than necessary. This could be exploited by the attacker. By looking at the spatial distribution of absolute gaze position on a certain visual scene, for example, by looking at this eye tracking heat map on this web page, the attacker could learn the user's implicit interest. Also, the attacker could exploit the aggregate statistic of distribution of eye gaze or the features of the eye gaze over time, for example, the saccade length. And this can enable the modeling of the user and leaks a lot of psychological and physiological traits. The psychological traits include the user interest implicitly and the cultural background and also personality traits and etc. This could enable the precision advertisement even without the user's consent. On the other hand, the physiological traits include health conditions such as Alzheimer's or vision correction condition, also biometric identity, and those are really private to the user as well. So here we know that there's a lot of privacy concerns or threats on using eye tracking data, but still we want to enjoy the real-time utility of eye tracking. So how can we have a generalizable eye tracking control to protect the privacy? However, the existing design to protect the privacy of eye tracking data provide no formal guarantee or only allow offline release. For example, they may rely on the aggregation of all the users' eye tracking features and add noise on the features before releasing the noisy feature to the application across the trust boundary. So this is not suitable for real-time applications. Therefore, we formulate our research question for KALEIDO. That is, how can we control the privacy while preserving the real-time utility of eye tracking? Here is an overview of KALEIDO's function. The user is interacting with the system that collects the raw streaming eye gaze. And the KALEIDO will add noise in an online manner on the individual gaze through the raw streaming data. And the KALEIDO can relay the noisy streaming eye gaze across the trust boundary to the application. So the application can see the data with the same format as before. So this will enable the application to offer the real-time utility to the user in parallel. So we can enjoy the formal privacy guarantee on eye gaze streams by local differential privacy in KALEIDO. And KALEIDO can be seamlessly integrated with real-time eye tracking applications in the nowadays ecosystems. And it's easy to use by ultimate privacy configuration. How can we define the privacy for KALEIDO? Recall that the format of eye tracking data or eye gaze data is essentially a location. Here, I show an example in 2D. So the KALEIDO's privacy guarantee is focusing on the spatial information of eye gaze, which is the primary source of sensitive attributes and information. We develop and leverage a slight variant of the geo-indistinguishability local differential privacy framework that has a noisy mechanism to ensure that for all pairs of inputs or gaze locations within a certain distance of R, which is also the radius of the collocating region, that the inputs can enjoy the indistinguishability with the probability allowed by the standard privacy epsilon or the privacy budget. On the other hand, we're not just focusing on protected privacy of one single IGATE. The realistic data format is a streaming IGATE, so we are protecting the privacy for the stream. How can we achieve that? The challenge is we're dealing with a non-deterministic stream in the real-time utility and interaction. By leveraging the WEM privacy with the geo-indistinguishability framework, we can protect the spatial distribution of any gate trajectory form over any sliding window of duration W through the infinite stream. With the privacy definition in hand, how do we implement KALEIDO in the real system? The KALEIDO has 4 major blocks. The first one is configuration manager that sets the privacy budget epsilon according to the user need, as well as the window length W according to the scene change frequency in the video stream, as well as the location indistinguishability radius R according to the spatial characteristic of the ROI in the keyframes. And then the context processing code can extract the ROI for setting the radius R. With the privacy parameter configured, we have this noisy gates generation algorithm that noise each row gates online. The challenge here is the iGates data is sampled at a high rate in the real world setting. So a naive budget allocation for the privacy project will harm the utility of the eye tracking data with the DP banner. Hence, by constructing the DP allocation algorithm with the semantics of human eye gaze in mind, we only release the noisy eye gaze when a new fixation is detected in a DP manner. Hence, we can preserve the utility of eye tracking data by saving the privacy budget while preserving and holding the privacy guarantee. Then we have the noisy gaze processor that allows local post-processing, such as smoothing, before offloading the data to the untrusted applications. Here, I intuitively show the effect of KALEIDO against the one without the privacy enabled, using the visualization of eye tracking data heat map on the web page. We can visually see the differences between different setups with and without privacy. However, we're also interested in the systematic evaluation of KALEIDO in different focuses. The first one is the user perception in real-world utility with KALEIDO. And the second one is impact of KALEIDO on system performance. And the last one, recall that the KALEIDO's privacy guarantee is on the spatial information of gaze streams. Here, we evaluate the effectiveness against attack that utilize the spatial temporal features of eye gaze, which are the realistic analytics and attacks in the real-world setting. We are interested to see how our privacy guarantee translates to the effectiveness against the real-world attacks. First, we show our setup for the user study. Here, we consider that the eye tracking game is a good example to evaluate the perception in the real world. Hence, we construct our eye tracking game with KALEIDO using Unity. In the game, the user's target is to take down the zombie rabbit using the laser beam aimed and directed by the eye gaze. Due to the COVID-19 constraint, we construct a remote user study with the PC webcam eye tracking game approved by our IRB. And we recruit 11 users, each with a study session about 35 minutes in total. We have 5 privacy settings evaluated in the anonymized and randomized order, except for the control node setup, where we allow the users to change their privacy setting during the gameplay. To evaluate the perception result, we first ask the user to report their subjective enjoyment level for the game with different settings. And then we record the game score or the numbers of rabbits taken during the game for each user. So from the result takeaway is we observe a negligible experience degradation with low privacy setup. But even with high privacy setup, KALEIDO poses minor impact on the user's perception and the game performance. How about the system impact? We use a commodity PC platform to run and execute KALEIDO. Here, comparing to the context processing, the noising step of KALEIDO takes negligible latency. The context processing includes the keyframe detection and the ROI detection on the keyframe using neural network. but the performance is not degraded greatly even at a really frequent context update rate of 8 Hz. Then, how about the effectiveness against spatial temporal features attack on user interest and biometric? First, we construct a tag on user interest using a dataset of PC eye tracking for viewing 30 unique images, each set with at least 19 users. The goal is to identify the users with distinct attention patterns per image by clustering or outlier detection. The conclusion from here is the attacker's success is brought to random guess at high privacy settings, even low privacy setting towards attack greatly. On the other hand, how about the biometric tags? The dataset we're using here is the VR eye tracking dataset during video sessions for 12 unique videos with multiple users. And we are set attacker to identify the user traits by classified trend on biometric features in unseen sessions with KALEIDO to learn their biometric identity as well as the vision correction condition. The takeaway is the attacker's success is brought to random guess again, even with low privacy configuration for both traits. To conclude, KALEIDO is the first system to protect the privacy of real-time eye tracking. And by deploying differential privacy, we leverage the semantics of eye gaze so that KALEIDO can be seamlessly integrated with the existing eye tracking ecosystems. Here's my contact. Welcome to ask us any questions, suggestions, or ideas. And we're looking forward to our future opportunity and collaborations in this field. Thank you very much for listening. That concludes my talk.